Welcome everyone, and welcome to the AluVET Vocational Training and Education for the Aluminium Sector. This training is co-funded by the Erasmus Programme of the European Union. I am Jan Lukaszewski, the Technical Manager of the Aluminium Federation in the United Kingdom. The Introduction to Metals series of modules explains the simple theory of metals and of metallurgy to enable students in subsequent modules to understand aluminium, its alloys, heat treatment, and how it is rolled, extruded, and/or welded. This project is funded with the support of the European Union. This publication reflects only the views of myself and the Aluminium Federation, and the Commission cannot be held responsible for the use which may be made of the information contained therein. This module explains how non-heat treatable aluminium alloys can be strengthened through strain hardening, and how annealing can be used to graduate the degree of strain hardening. This module will explain what tempers are and their designations, and which alloys cannot be strengthened through heat treatment. You will learn how non-heat treatable alloys can be strengthened through strain hardening, and about how the degree of strain hardening increases strength. Finally, you will learn about how annealing restores ductility to strain hardened alloys. Having completed this, you will be able to specify the correct temper and the required treatment to achieve your required product strength properties. This module uses very simplified explanations of strain hardening and of annealing. It is intended to provide sufficient understanding of strain hardening and annealing and their effects, rather than full metallurgical explanation of the actual mechanisms. The European standard EN 515 describes all the possible heat treatment and methods of strengthening aluminium alloys. The different aluminium heat treatments are termed tempers. European standard EN 515 lists all of the commercially available tempers and summarizes their methods of strengthening aluminium alloys. This standard is applicable to all forms of wrought aluminium and aluminium alloys. In the European standard EN 515, additional designations are added after the four-number alloy chemistry designation. The additional designations explain how the physical properties of the wrought aluminium are modified by heat treatment and all the mechanical heat treatments. In the example you're looking at, 5052 is the four-number chemistry series, and after that you will see a letter H and some numbers. The first letter of the designation indicates the treatment applied, the heat treatment applied to produce the properties. So O is annealed, used after cold working to soften work hardenable aluminium alloys, the 1000, the 3000, the 5000 series. The letter H says this is strain hardened, cold worked, remember. This applies to non-heat treatable alloys, the 1000 series, the 3000 series, the 4 and the 5000 series that are cold worked or strain hardened. T says this is heat treated. This applies to the alloys strengthened by heat treatment. The 2000, the 6000 and the 7000 series. In this module, we will be talking about the 1000, the 3000 and the 5000 series. Now, the 1000 series, pure aluminium, the 3000, the 4 and 5000 series can only be strengthened by cold work or strain hardening. They can subsequently be softened by annealing. But the 1000, 3, 4 and 5000 series cannot be strengthened by heat treatment. In the strain or work hardened condition, the 1, 3, 4 and 5000 series can be softened by annealed. So I need you to understand that the 1000 pure aluminium, the 3000, 4 and 5000 series are not heat treatable alloys. They can only be, their strength and properties can only be changed through strain hardening or work hardening. So we can only strengthen non-heat treatable aluminium alloys by strain hardening or cold working. During cold working, as the degree of slip increases with increase in cold work, the deformation of the grains becomes more severe. As the severity of the deformation increases, the new flattened shape is more resistant to further deformation. The forces required to induce more slip, more shape change, increase with increase in deformation. Thus, cold work and the resultant slip causes a strength increase. Increase in the degree of strain hardening thus increases the yield and tensile strength. And we term this cold work strength increase work hardening or strain hardening. The greater the cold deformation, the higher the strength increase. Now remember that ductility is the reciprocal of strength, so that the greater the strength resulting from work hardening, the lower will be the ductility, as you can clearly see in the graph. For the non-heat treatable alloys, European standard EN 515, temper codes designate cold or strain hardening by using the letter H, followed by numbers. And H1, followed by numbers. The first number indicates how the temper was achieved. In this case, the number H1 indicates that the cold worked or that the alloy is in the cold worked or strain hardened condition. So the 1000, 3, 4 and 5,000 can only be strengthened by work hardening. The standard EN 515 designates strain hardening using the letter H, and then number 1 says that this alloy is in a cold worked or strain hardened condition. The second number after the H1 indicates the degree of strain hardening. So there is a second number after the number 1, and that indicates the degree of strain hardening. That is the amount of strain hardening, and it's an indication of the resultant yield and tensile strength increase. So H12, 1, 2, indicates a strain hardened alloy to the quarter hard condition. H14 is strain hardened to a half hard condition. H16 indicates strain hardened 3/4 hard. And H18 indicates strain hardened to a fully hardened condition. So H is strain hardened. The 1 says this is in the strain hardened only condition. The numbers 2, 4, 6 indicate the degree of strain hardening. Now in this graph, in this slide, please see a graph of strength against strain on the right hand side, where strain is a measure of strain hardening, and on the left hand side the vertical axis is strength. The left hand vertical axis is a measure of ductility. So on the left we're measuring strength. Across the axis we're measuring the degree of work hardening. On the right hand side we're measuring ductility. Now in this slide, we've got a micrograph of a fully annealed aluminium alloy in the O condition. So it has minimal strength. And you'll notice that the annealed grains are equiaxed. And on the right-hand side of the graph, just below the number 50 is the strength indication of that alloy. So we've got an annealed alloy in the O condition. Now, in this slide, we've got a micrograph of an alloy that has been strain hardened to a quarter hard condition. Quarter hard is a minimal amount of strain hardening. Note that the grains have been deformed, so they're elongated, and also note that their deformation has resulted in an increase in strength. So please note the H12 plot on the graph. In this slide, we have now strain hardened our alloy to a half hard condition, the H14 strength. You can see that the grains have been plastically deformed, stretched. So now we can see marked permanent elongation, plastic deformation of the grains. The higher deformation of the half hard condition has strengthened the alloy to the H14 plot on our graph. As the degree of strain hardening continues to increase, so the degree of work hardening continues to increase, the deformation of the H16 grains, 3/4 hard condition, is now very significant, with the grains being totally distorted and permanently elongated. And the significant deformation increases the strength to the H16 plot.